Continuing our discussion on the structural analysis and structural design of industrial chimneys subjected to wind loading, as mentioned earlier, the wind exerts an along wind force as well as crosswind force due to the drag and lift that are induced on any single stationary bluff body, obstructing a streamlined flow of fluid based on the first principles of first mechanics. The drag and the lift thus result in an along wind force as well as an across wind force acting on the chimney. The crosswind load that acts on the chimney due to the transverse or the crosswind component of the wind pressure distribution around the periphery of the cross section of the industrial chimney may be critical in governing the structural design of the chimney shell under certain conditions. And since the crosswind loading may govern or dictate the structural design of the chimney shell, the crosswind loads acting on the industrial chimney need to be calculated and accounted for in the wind resistant design of the industrial chimney. Calculation of the crosswind load acting on the industrial chimney structure is performed in accordance with the simplified procedure that is provided by IS 4998 Part 1, that is the Indian Standard Code of Design Practice for circular cylindrical chimneys under the action of wind loads. The methodology of computing the crosswind loads for the purposes of the structural design of the industrial chimney for wind loading in accordance with the simplified procedure provided by IS 4998 Part 1 may be summarized by the following steps. Step 1. Compute the critical wind speed denoted as VCRI, where the notation V represents the wind speed while the subscript CR denotes the critical wind speed and the subscript I denotes the mode of vibration, that is the mode of free vibration response of the industrial chimney. And the definition of critical wind speed is the wind speed that is required to excite the first or the fundamental mode of free vibration response represented by the mode shape phi 1 for I equal to 1, that where I is the mode number of the free vibration response of the industrial chimney. Since the fundamental or first mode of the free vibration response is the lowest energy mode, that is lowest or the least amount of energy in the form of kinetic energy from the wind is required to excite or activate the first mode of vibration, and larger amounts of energy are required to excite the higher modes, that is the modes 2, 3, 4 and further, which require greater input energy or higher kinetic energy from the wind for excitation of these higher modes, and therefore the critical wind speed that is required to excite the first or the fundamental mode of free vibration, that is mode number I equal to 1, is calculated as VCR1 for I equal to 1 to determine whether the wind or the wind flow around the cross section of the industrial chimney excites or activates the first or the fundamental mode of free vibration or not. It is worthwhile to mention here that the higher modes, that is modes 2, 3, 4 and higher modes, require greater or input energy or higher kinetic energy from the wind for excitation of these higher modes, since the higher modes 2, 3, 4 and so on are associated with higher strain energy or higher potential energy, with the potential energy or strain energy increasing with the mode number, and thus the input energy or the kinetic energy that is required for the wind for exciting these higher modes increases with the mode numbers, thus resulting in the first or the fundamental mode of free vibration response of the industrial chimney structure, that is the mode shape phi 1 for I equal to 1, is the critical mode of free vibration response for a crosswind loading, and the critical wind speed VCRI for I equal to 1, that is the first mode or the fundamental mode of free vibration response, is therefore required to activate the crosswind response of the industrial chimney structure. Calculating the critical wind speed VCRI for I equal to 1, that is the critical wind speed VCR1 that is required to excite the first or the fundamental mode of free vibration response, phi 1 of the industrial chimney structure, the critical wind speed is then compared with the design wind speed on the site. And if the critical wind speed VCR1 for the first or fundamental mode of free vibration response of the industrial chimney structure is greater than the design wind speed on the site of construction of the industrial chimney, then a crosswind response is not excited or activated and thus need not be considered. On the other hand, if the design wind speed at the site of construction of the industrial chimney is greater than the critical wind speed VCR1 that is required to excite the first or the fundamental mode of free vibration response of the industrial chimney structure, then the crosswind response or crosswind vibrations of the industrial chimney will be induced or activated, and thus a crosswind vibrations or a crosswind response need to be calculated for the computed crosswind load. Well, step 1 may be completed by performing a few sub-steps or tasks. That is, first task A is to therefore compute the natural period or the fundamental time period T1 of the first mode of free vibration response of the chimney, idealizing the chimney as a single degree of freedom oscillator with a single lumped mass, say denoted as capital M, mounted on a cantilever that is weightless beam with free fixed end conditions. The cantilever model with the chimney mass M, capital M, concentrated at the free end of the weightless cantilever with the natural circular frequency of the single degree of freedom model, thus idealized, denoted as omega, given as 2 pi by T1, that is the natural circular frequency omega of the single degree of freedom model, idealizing the chimney structure, is related to the fundamental time period or the natural period T1 of the first mode of vibration, or that is the first mode of free vibration response of the industrial chimney structure. And based on the first principles of structural dynamics and simple harmonic motion, the natural circular frequency omega of the single degree of freedom model, idealizing the industrial chimney structure, may be computed as the square root of the stiffness of the single degree of freedom oscillator, that is the lateral stiffness of the weightless cantilever, divided by the lumped mass or the mass M of the chimney that is assumed to be concentrated or lumped at the free end of the single degree of freedom oscillator that is considered to model the industrial chimney structure. Hence, given the fundamental time period or the time period T1 of the first mode of free vibration response of the practical or real industrial chimney structure, also termed as the natural period of the practical or real industrial chimney structure, as denoted as T1, which may be available from experimental measurements or vibration analysis. The vibration analysis of the industrial chimney structure in the field, the stiffness K of the single degree of freedom oscillator, that is the lateral stiffness of the weightless cantilever in the single degree of freedom model, that is considered to idealize or represent the real or practical industrial chimney structure, may be calculated as 4 pi square times the mass M of the chimney divided by square of the fundamental time period or the natural period T1 of the practical or real industrial chimney structure, in order to determine the dynamic properties or the dynamic characteristics of the mathematical model, that is the single degree of freedom oscillator representing or idealizing the real or practical industrial chimney structure for purposes of dynamic analysis. The fundamental time period T1 of the first mode of free vibration response of the real or practical chimney, or the also termed as the natural period of the real or practical industrial chimney structure, may either be measured experimentally in the field by performing a vibration analysis of the ambient vibrations of the industrial chimney structures in the field. In the absence of experimental or field data, the field measurements of the vibration response of the industrial chimney structure, the semi-empirical formulation that is provided by standard textbooks for estimating the fundamental time period of the first mode of free vibration response of the chimney, termed as the natural period of the real or practical industrial chimney structure, may be employed, and the semi-empirical formulation that is one of the most reliable estimates of the natural period or the fundamental time period T1 of practical or real industrial chimney structures as recommended by many textbooks is mentioned on the current slide, which estimates the natural period or the fundamental time period T1 of the first mode of free vibration response of a real or practical industrial chimney structure as a coefficient Ct divided by 3.1 factor, that is numerical factor 3.1 times the square root of the weight of the chimney, that is the total weight W of the chimney structure, times the height of the industrial chimney structure divided by the elastic modulus of concrete in case of reinforced concrete chimneys, and times the area of cross section of the chimney shell at the base of the chimney. Hence, in the absence of reliable field measurements or field data, experimental data for vibration analysis of real practical industrial chimney structures, to determine the real or actual fundamental time period T1 of the free vibration response of the real or practical chimney, experimentally one may employ the semi-empirical formulation that is presented in the current slide, which is one of the most reliable semi-empirical formulations that is recommended by textbooks. In the scope of the present course, for the purposes of the acrosswind analysis of industrial chimney structures, that is calculation of acrosswind load acting on the industrial chimney structures and the resulting acrosswind vibration response of the industrial chimney structures, we will be applying the same semi-empirical formulation that has just been discussed and is presented on the current slide. The second sub-step, as mentioned earlier, to complete the step 1 of the methodology of calculating the crosswind load acting on the industrial chimney structure and the resulting crosswind vibration response of the industrial chimney structure is B, and in sub-step task B, the critical wind speed, that is the wind speed that is required to excite or activate the first or the fundamental mode of free vibration response described by the mode shape phi1 is calculated based on the natural period or the fundamental time period T1 that is obtained from the semi-empirical formulation as discussed in substep A. And clause A 4.3 of IS 4998 Part 1, the Indian Standard Code of Design Practice for calculation of wind loads on industrial chimney structures, provides the relationship between the critical wind speed denoted as VCRI for any general mode of free vibration response I of the industrial chimney structure with the linear frequency of free vibration denoted as Fi corresponding to the mode of free vibration response I that is under consideration, and the critical wind speed denoted as VCRI for the ith mode of free vibration response of the industrial building structure that is required to excite the ith mode of free vibration response phi I in general of the practical or real industrial building structure is specified, given by the simplified procedure provided by IS 4998 Part 1 in clause A 4.3 as Fi times D divided by parameter Sn, where Fi, as mentioned earlier, is the linear frequency of the free vibration response for the ith mode of free vibrations that is under consideration and may be calculated simply as 1 over the time period, that is the natural period or the fundamental time period Ti of the ith mode of free vibration response of the industrial chimney structure. Now, since the lowest amount of energy, that is the lowest amount of kinetic energy or input energy is required from the wind for exciting the first or the fundamental mode of free vibration response described by the mode shape phi1 for the fundamental reasons discussed earlier. The critical wind speed VCR1 for the first mode of free vibration response of the industrial chimney structure is the one of interest, and therefore we need to calculate only the critical wind speed VCRI for I equal to 1, that is the critical wind speed, that is VCR1, that is required to excite the first or the fundamental mode of free vibration response of the industrial chimney structure. as the first mode or fundamental mode of free vibration response is the lowest energy mode, requiring the least amount of input kinetic energy from the wind to be excited, and thus is the first mode of the free vibration response, that is mode I equal to 1, is the only relevant mode to determine whether the crosswind vibration response will be excited or not. Therefore, in substep B, calculating the critical wind speed VCR I for I equal to 1, that is the critical wind speed VCR1 for the first mode I equal to 1 of the industrial building structure, industrial chimney structure, using the formulation provided by clause A 4.3 of IS 4998, in which the linear frequency F1 of the first mode, that is mode I equal to 1 of the free vibration response of the industrial chimney structure, is simply calculated as the reciprocal of the fundamental time period T1, or the natural period of the free vibration response of the industrial chimney structure, as calculated from the semi-empirical formulation provided in substep A. Then, therefore, comparing the critical wind speed VCR1 that is required to excite the first or the fundamental mode of free vibration response for the mode I equal to 1 with the design wind speed Vz at the site as stipulated by the IS 875 part 3 at the height Z equal to the physical height of the chimney. If the design wind speed denoted as Vz at the height Z equal to the physical height HP of the chimney as specified by the Indian Standard Code of Design Practice for Calculation of Wind Loads, IS 875 part 3, is greater than the critical wind speed VCRI for the first mode, or the mode I equal to 1 of the free vibration response of the industrial chimney structure as calculated above. Then one can assume that the crosswind vibration response of the chimney structure will be excited or activated, and thus we need to calculate the crosswind load on the chimney as well as the related crosswind vibration response of the industrial chimney structure. Otherwise, that is, in case the design wind speed Vz at the site of construction of the chimney at height Z equal to the physical height of the chimney as given by IS 875 part 3 is less than the critical wind speed VCR1 that is required to excite the first or the fundamental mode of free vibration response I equal to 1 of the industrial chimney structure, then a crosswind vibration response of the chimney structure will not be excited or activated, and hence the crosswind response may be neglected, and consequently a crosswind loads or crosswind loading on the chimney structure need not be calculated, since the wind or airflow at the site of construction of the industrial chimney structure will not be able to mobilize or generate sufficient kinetic energy due to the insufficient or inadequate design wind speed to excite or activate the first mode of the crosswind vibration response of the industrial chimney structure, which may therefore be neglected if the design wind speed Vz at the height Z equal to the physical height of the chimney Hp at the site of construction of the industrial chimney is less than the critical wind speed Vcr1 that is required to excite the first or the fundamental mode I equal to 1 of the free vibration response characterized by the mode shift phi1 of the industrial chimney structure. Continuing our discussion on the calculation of crosswind loads acting on industrial chimneys and the related crosswind vibration response exhibited by the chimney shell, it is worthwhile to note here that tall chimneys with heights equal to or greater than 100 meters as the physical height of the chimney generally exhibit a crosswind vibration response, since the critical wind speed Vcr, that is for the first mode of the free vibration response of the chimney shell, is generally lower or lesser than the design wind speed at the site of construction of the industrial chimney. Hence, tall chimneys with heights equal to or more than 100 meters exhibit a crosswind vibration response, since the first mode of the free vibration response of industrial chimneys with physical heights equal to or greater than 100 meters is excited or activated by the design wind at the site of construction of the industrial chimneys. In fact, for chimney heights, that is the physical height of the industrial chimneys greater than 100 meters above the mean ground level, the crosswind response and therefore the crosswind loads may be critical in the determination of the structural design of the chimney shell. In other words, for industrial chimneys with physical heights greater than 100 meters, the crosswind response due to the crosswind loading stipulated by IS 4998 Part 1, the Indian Standard Code of Design Practice for calculation of wind loads on circular cylindrical industrial chimneys, may be critical or predominant in governing the structural design of the chimney shell. Therefore, step 1 of the simplified procedure, that is provided by IS 4998 Part 1 for calculations of crosswind loading, is a crucial step in determining whether the crosswind loads are critical in the structural design of the industrial chimneys. Further, in case the design wind speed at the site of construction of the industrial chimney is found to be greater than the critical wind speed denoted as VCR as presented in the previous slide, where VCR is the critical wind speed for the first or the fundamental mode of free vibration response of the industrial chimney. Then the crosswind loading must be considered and computed to determine the crosswind vibration response of the industrial chimney, as the crosswind loads, the related or resulting crosswind vibration response of the industrial chimney may govern the structural design of the chimney shell. To step 2 of the exercise of calculating the crosswind loads based on the simplified procedure provided by IS 4998 Part 1. In the step 2 of the calculation of crosswind loads, the peak tip deflection denoted as mu I or VIT based on the first mode, that is I equal to 1 of the crosswind vibration response is calculated based on the assumed mode shape described by the mathematical function phi1z for the first mode of free vibration response of the chimney shell, that is depicted visually in the figure presented on the current slide. And since the mathematical model for the industrial chimney is idealized as a concentrated mass denoted as capital M, that is assumed to be lumped or concentrated at the top of a weightless cantilever, where the concentrated mass capital M is the total mass of the chimney structure, the mode shape function corresponding to the first mode of free vibration response of the chimney shell is therefore a parabolic function based on the deflection profile of a cantilever or a beam with free fixed end conditions. Noting that the maximum value of the deflection at the free end of the single degree of freedom model that is used to idealize the chimney shell is 1 or unity for any mode shape, including the mode shape 1, and the base of the cantilever, that is the base of the chimney shell at the ground, is idealized to be fixed against deflections as well as rotations, substituting the boundary conditions at the free end and the fixed end of the idealized single degree of freedom model, consisting of the lumped mass of the chimney structure denoted as capital M, concentrated at the top of the weightless cantilever, with the other end of the cantilever being a fixed end, may be considered to result in the mode shape function phi1z for the first mode of free vibration response of the chimney shell or the idealized single degree of freedom model as z square over h square, where z is the height above the ground in case of the real or practical industrial chimney, and is the distance from the fixed end in case of the idealized single degree of freedom model consisting of the lumped mass M concentrated at the top of the weightless cantilever. In the next step, that is step 3, we calculate the maximum bending moments and shear forces in the chimney shell denoted as MZ01 and FZ01 respectively, as per clause A.4.2.1 of the simplified procedure, that is provided by IS 4998 part 1, wherein the maximum bending moment MZ01 and FZ01 are the longitudinal or meridional bending moments in the chimney shell, while FZ01 is the related shear force in the chimney shell, in which the subscript 1 signifies that the maximum bending moment MZ01 and the maximum shear force FZ01 corresponds to the first mode of free vibration response of the industrial chimney. It may be noted here that equations provided in clause A4.2.1 of the simplified procedure stipulated by IS 4998 part 1 for calculation of crosswind loads are based on the theory of simple harmonic motion, that is, the equations of the dynamic response of a single degree of freedom mass spring oscillator, and hence concluding the exercise of calculating the crosswind vibration response and response parameters that are of interest from the point of view of structural design, which are the maximum longitudinal bending moment or meridional bending moments MZ and the related maximum shear forces FZ in the chimney shell as per clause A4.2.1 of IS 4998. To our discussion on the calculation of crosswind loads and the related crosswind vibration response of circular cylindrical industrial chimneys as specified by the simplified procedure provided by IS 4998 Part 1, the Indian Standard Code of Design Practice for calculation of wind loads on circular cylindrical chimneys. The methodology for calculating the crosswind loads in accordance with the simplified procedure is quite mechanical and routine, since the steps 1, 2 and 3 discussed in the previous and the present slide need to be simply followed by substituting the numerical values of the industrial chimney into the design formulations or the design equations that are provided by the simplified procedure for calculating the crosswind loads and computing the various successive design parameters that are specified by the simplified procedure provided by the code IS 4998 part 1 sequentially to arrive at the maximum longitudinal and meridional bending moment and the related maximum shear force as per clause A 4.2.1 of IS 4998. Proceeding to the next topic, or next design loading that needs to be considered for the structural design of industrial chimneys. The next type of design loading that is equally important to be accounted in the structural design of industrial chimneys is the earthquake loading. That is the loading due to seismic effects on chimneys. Since chimneys are particularly vulnerable to earthquakes, being tall and massive structures, and the calculation of earthquake loads on industrial chimney structures is based on the response spectrum method specified by IS 1893 part 1, the latest revision, that is the 2016 revision for seismic analysis of the industrial chimney structure. The seismic analysis, that is defined as the structural analysis of the chimney structure or chimney shell to calculate the earthquake forces or the seismic forces, follows a step-by-step procedure based on the application of the response spectrum method provided by clause 6 of IS 1893 part 1. Idealizing the chimney again as a weightless cantilever with fixed free end conditions and a lumped mass M equal to the total mass of the chimney structure concentrated at the top of the cantilever, or alternatively a more advanced or sophisticated mathematical model may be employed, which consists of a cantilever with distributed mass representing the chimney shell, by assigning the representative geometric properties such as the area of cross section, second moment of area, or the moment of inertia of the real or actual chimney shell to the cantilever, with variation of such geometric properties over the height of the cantilever to account for the taper that is typically incorporated in practical or real chimney structures. Now, it is worthwhile to note that earthquake loading may, under certain conditions, govern the structural design of the industrial chimney structures, as chimneys are particularly tall and massive structures and thus particularly vulnerable to earthquakes. Therefore, it is important or crucial to consider earthquake loads in the structural design of industrial chimney structures in accordance with the clause 6 of IS 1893-2016, the Indian Standard Code of Design Practice for earthquake resistant design of structures. Proceeding with the calculation of earthquake loads acting on industrial chimney structures for the purposes of earthquake resistant design of industrial chimneys in accordance with the Indian Seismic Design Code IS 1893 Part 1 2016, that is the Indian Standard Code of Design Practice for earthquake resistant design of structures. The earthquake loads acting on chimney structures that need to be accounted in the structural design of the chimney shell are calculated by performing a seismic analysis of the chimney shell based on the response spectrum method provided by IS 1893 for seismic analysis of structures, that is, the structural analysis of industrial chimneys to calculate the design earthquake forces for the purposes of structural design of industrial chimneys. And the response spectrum method that is stipulated by the Indian Standard Code of Design Practice for earthquake resistant design of structures IS 1893 follows a few simple steps, the step-by-step methodology for the application of the response spectrum method provided by IS 1893 for seismic analysis of industrial chimney structures in order to calculate the design earthquake loads or the design seismic forces acting on the chimney shell for the purposes of structural design may be summarized as follows. Step 1. To calculate the fundamental period or the natural period defined as the time period of the first mode of free vibration response of the chimney structure. As an example, in case of building structures, the Indian Standard Code of Design Practice for earthquake resistant design criteria of building structures specifies the fundamental time period or the natural period, that is the time period of the first mode of free vibration response of building structures, as 0.09 h over under root d for a building structure with reinforced concrete shear walls or brick infill frames. In case of industrial chimney structures, since the structural system of industrial chimneys, that is the specific case of circular cylindrical industrial chimneys with a cylindrical shell as the structural system, the natural period of a practical continuous chimney structure consisting of a circular cylindrical shell may be computed using any realistic formulation based on a rational analysis method or experimental measurements or field test results or both. For the purposes of the present course, we will apply the same semi-empirical formulation that was used or implemented to calculate the fundamental time period or the natural period of the industrial chimney structure for the purposes of calculating the crosswind loads and the related crosswind response as presented in one of the earlier slides. And to refresh your memory, the semi-empirical formulation that is found to be reliable and rational for estimating the fundamental time period or the natural period of an industrial chimney structure with a circular cylindrical shell and is also recommended by standard textbooks, provides the time period of the first mode of free vibration response T1 of the industrial chimney structure as CT coefficient divided by 3.1, another factor or coefficient, times square root of the weight, that is the seismic weight of the industrial chimney structure, times the height of the chimney structure divided by the elastic modulus of concrete times the area of cross section of the chimney shell at the base of the industrial chimney structure in case of circular cylindrical chimneys in SI units or Newton meter units. In the semi-empirical formulation presented above, and also in one of the previous slides, for computing the natural period or the fundamental time period, that is the time period T1 of the first mode of vibration in the free vibration response of a circular cylindrical chimney structure, the coefficient C subscript T depends on the slenderness ratio of the chimney shell or the chimney structure, that is defined as the height of the chimney structure divided by the minimum radius of gyration of the chimney structure, which is the minimum radius gyration of the chimney cross section at the base of the industrial chimney. In case of circular cylindrical chimney structures, the parameter R subscript minimum, that is R subscript min, is the only radius of gyration of the circular cylindrical chimney shell at the base of the industrial chimney structure, since a circular cylindrical shell has only one radius of gyration and the other radius of gyration is equal to the first radius of gyration, and therefore the minimum radius of gyration R minimum, that is R subscript min, is the same as the only one radius of gyration in case of circular cylindrical shapes, while the variable or parameter capital W is the weight of the chimney, including the lining and accessories of the chimney, and the area of cross section denoted as A subscript C of the chimney that is considered in the semi-empirical formulation for calculating the fundamental time period of the industrial chimney structure is the cross-sectional area of the chimney shell at the base of the industrial chimney. In step 2, calculate the horizontal seismic base shear coefficient denoted as A subscript H for the industrial chimney structure as per clause 6.4.2 of IS 1893 part 1 latest 2016 revision, that is the Indian standard design criteria for calculation of earthquake loads on structures, which provides the horizontal seismic base shear coefficient in accordance with clause 6.4.2 as the familiar and well-known formulation, that is the seismic zone factor Z divided by 2 times the spectral acceleration normalized with respect to acceleration due to gravity divided by the response reduction factor R over the importance factor I of the industrial chimney. And the importance factor of industrial chimneys is to be considered as 1.5, that is the importance factor for important structures, since industrial chimneys are critical structures. Further, as per clause 7.2.1 of IS 1893, the latest 2016 revision, that is the Indian Standard Code of Design Practice for earthquake resistant design of structures, the design lateral force on the industrial chimney structure, denoted as capital V subscript H, may be simply calculated as the product of the horizontal seismic base shear coefficient A subscript H times the weight of the chimney, including the lining and accessories of the chimney. In step 3, we compute the design bending moments, which are the longitudinal or meridional bending moments in the terminology of the theory of cylindrical shells, denoted as M subscript X in the context of earthquake loading or seismic effects on chimney structures, as well as the transverse shear forces denoted as V subscript X related to the design bending moments, that is the longitudinal or meridional bending moments Mx, using the formulations provided based on semi-empirical considerations, that is, considerations of both theoretical or practical behavior, as well as past experience based on field measurements or experimental data. It is worthwhile to note here that the design bending moments that provide the design or the maximum values of the meridional or longitudinal bending moment mx at any distance x dash from the top of the chimney equals the base shear, that is the horizontal seismic base shear V subscript h, calculated as the product of the horizontal seismic base shear coefficient times the weight of the chimney, including lining and accessories, times the height of the CG of the real or practical industrial chimney above the ground level, denoted as H over bar, times a function of the coordinate x dash, which is defined for the purposes of this formulation as the distance from the top of the chimney. Therefore, substituting x dash, that is the distance from the top of the chimney at which the design bending moment is to be calculated, as equal to the height of the chimney, the coefficient in the square parenthesis in the design formulation presented in the current slide for the design bending moment mx is exactly equal to 1, thus resulting in the value of the design bending moment mx, that is the design value of the meridional or longitudinal bending moment at the base of the shell, that is at x dash equal to h, where x dash is the distance from the top of the chimney, equal to the horizontal seismic base shear V subscript h times the height of the CG, center of gravity of the industrial chimney structure, which is reasonable and rationally justified, since one would expect that the design bending moment mx at x dash equal to h, that is the design bending moment at the base of the industrial chimney structure, should equal to horizontal seismic design base shear V subscript h, that is deemed to be acting through the center of gravity of the industrial chimney structure, times the height h over bar of the center of gravity or CG of the industrial chimney structure. Since the design lateral seismic force acting on the chimney, denoted as V, capital V subscript h, is equal, opposite to the design horizontal seismic base shear at the base of the chimney shell, and therefore the design lateral seismic force acting on the chimney structure, denoted as capital V subscript H, and the design horizontal seismic base shear, calculated as the product of the horizontal design seismic base shear coefficient A subscript H times the weight of the industrial chimney structure with lining and accessories should be equal and opposite, and therefore same in magnitude. Further, it may be noted that the design formulation provided in step 3 for computing the transverse design shear force, denoted as V subscript X, at any coordinate x dash, where x dash is the distance from the top of the chimney, which is the transverse shear force Vx related to the design bending moment Mx, presents a new coefficient that is denoted as C subscript V, where the subscript V signifies that the coefficient is for the computation of the transverse shear force related to the design bending moment Mx, and the subscript V therefore denotes the shear force, and the notation C subscript V signifies the coefficient is for the calculation of the transverse design shear force V subscript X. As a check, one may verify that substituting a value of the coordinate x dash, that is the distance from the top of the chimney, equal to the total height h of the chimney, into the formulation for the design transverse shear force Vx, which is the outer planar plate shear force related to the meridional moment Mx in the terminology of theory of shells, results in the value of unity or 1 for the terms in the square brackets, thus resulting in a value of the design transverse shear force Vx at x dash equal to h, that is at the base of the industrial chimney structure, equal to the coefficient C subscript V times the design horizontal seismic base shear AH times W, or the coefficient CV, that is C subscript V, times the design lateral seismic force acting on the industrial chimney structure. In conclusion of our discussion, on the calculation of earthquake loads or seismic forces that are to be considered for the earthquake resistant design of industrial chimney structures based on the response spectrum method for seismic analysis of industrial chimney structures for the purposes of calculating the earthquake induced forces or seismic forces and the resulting internal actions in the cylindrical shell structure of the industrial chimney comprising of the design bending moments, that is the design longitudinal or meridional bending moments mx at any coordinate x dash from the top of the chimney, and the design transverse shear forces Vx related to the design longitudinal or meridional bending moments mx at any coordinate x dash, where x dash is the distance from the top of the chimney as expressed by the design formulations presented in step 3 mentioned in the previous slide. The rotation h over bar is the height of the center of gravity of the chimney above the base or the ground level, and it may be noted that coefficient C subscript P that appears in the design formulation for the transverse design shear force Vx that is related to the design longitudinal or meridional bending moment mx also depends on the slenderness ratio of the chimney, defined as the parameter k, which is calculated as the ratio of the total physical height of the chimney h divided by the radius of gyration of the circular cylindrical shell in case of circular cylindrical industrial chimneys. Mathematically, the radius of gyration r of the cylindrical shell in the circular cylindrical industrial chimney structure is obtained as the square root of the moment of inertia of the chimney shell at the cross section of the industrial chimney at the base of the chimney structure, denoted as I subscript C, that is the second moment of area of the chimney shell at the base of the chimney structure, divided by the area of cross section of the chimney shell at the base of the industrial chimney. Finally, the coefficients C subscript T and C subscript V that appear in the design formulations presented in the previous slide for calculating the design bending moments, that is the design longitudinal or meridional bending moments based on the semi-empirical formulation for the natural period or the fundamental time period, that is the time period of the first mode of free vibration response of the industrial chimney structure, which is the coefficient C subscript T, as well as the coefficient C subscript V, which appears in the design formulation for the design transverse shear force V in the previous slide, are related to the slenderness ratio defined by the parameter K equal to the ratio of the total physical height of the chimney H to the radius of gyration of the circular cylindrical chimney shell at the base of the industrial chimney structure, which may be calculated as the square root of the second moment of area or the moment of inertia of the chimney shell at the base of the industrial chimney structure to the area of cross section A subscript C at the base of the industrial chimney structure. Hence, the table presented in the current slide provides the values of the semi-empirical coefficients denoted as C subscript capital T and C subscript V as functions of the slenderness ratio denoted as capital K, defined as the ratio H by R. For the sake of completeness, the final step, that is step number 4, that needs to be executed or performed in order to complete the calculation of all the design loading combinations that need to be considered for the structural design of the chimney shell in the industrial chimney structure. That were mentioned in one of the earlier slides. For example, the design loading combinations comprising of the combination of the dead load and the earthquake load, or dead load, earthquake load, and temperature load, will be included in the present discussion as a conclusion to the methodology of calculation of the various design loading combinations that need to be accounted for in the structural design of the chimney shell in case of industrial chimneys. Therefore, as a concluding remark, in step 4 of the methodology of calculating the design loads for the purposes of structural design of the chimney shell in industrial chimney structures, we calculate the combined internal actions such as the meridional or longitudinal moment mx, the related transverse shear force Vx, the circumferential bending moment m theta, and the hoop or the internal axial force n theta in the chimney shell due to the design loading combinations specified by the Indian design criteria for circular cylindrical reinforced concrete industrial chimneys and the Indian Standard Code of Practice for design of circular cylindrical chimneys, IS 4998 Part 1, for the various design loads, including earthquake loads or seismic forces. In case of the design loading combination consisting of earthquake loads or seismic effects, the design loading combinations, as mentioned in one of the earlier slides, that need to be considered for the structural design of the chimney shell in case of the industrial chimney structure are the design loading combinations consisting of dead load and earthquake load, and dead load and earthquake load and temperature load. In case of wind loads, the relevant design load combinations that need to be considered For the structural design of the chimney shell in case of industrial chimney structures are the dead load and the wind load, and the dead load, wind load plus the temperature load. Therefore, as mentioned earlier, only one of the two lateral loads, that is either earthquake load EL or the wind load WL, are considered in the structural design of the chimney shell due to the physical reasoning that the design wind and the design earthquake are unlikely or improbable to occur at the same time. Finally, the section dimensions and the steel reinforcement of the chimney shell are determined in the final stage of the structural design process, that is based on the structural design and detailing of the chimney shell, in which the dimensions, proportions, and the steel reinforcement area of the chimney shell are provided for the